Hello Honors Chemistry and welcome to Vesper Theory, which is the last couple sections of Chapter 9, where we take our Lewis structures, right, so the things that we've been doing in the first part of Chapter 10, which are two-dimensional, right, and simply show atoms and the things and the distribution of electrons around those atoms, and now we can assign a three-dimensional shape to those atoms, to those molecules, which is then going to allow us to determine if molecules are polar or nonpolar, right? Which is obviously very important because we've been alluding to that all year, right? You guys have been talking about that since middle school about how water is polar and polar things dissolve in water. Well, how do we know if something's polar? This is how we know. All right, so when we talk about Vesper, right, we are talking about valence shell, electron, right, pair. So first of all, only valence shell electron pairs are being discussed here, right? And then the R stands for repulsion, right? So we are saying that valence shell electron pairs repel each other, right? Okay, so this is the Vesper table from your guys' book. Well, first, let's go over what these different columns are, right? Actually, you know what? We're just going to use the Vesper table that I posted on PowerSchool, right? Which is akin to this one, right? And they share the same basic information. So this is the one that's in your book. This is the one that's on PowerSchool, and it shares all the same information, just more, right? So first, let's talk about what's here. So this is the groups around the central atom. So we always have to pick just the central atom. The vast majority of molecules that we draw have a singular central atom. For molecules that are bigger than that, we would just have to evaluate every atom as we go, all right? And the number of groups around the central atom then dictates the electronic geometry, okay? Where electronic geometry is the arrangement of all groups around the central atom. And by groups, right, things that qualify as groups are lone pairs, right, or a single bond, or a double bond, or a triple bond. And so note that each of these things counts as a group, yes? Each of these things counts as a group, all right, around the central atom. Now, then we have our molecular geometry, right, which is based on your atoms and lone pairs, and this molecular geometry gives us the shape of the atoms, which means that we are excluding lone pairs here in the shape, okay? So if we have no central atom, right, which means we're talking about only two atoms, right, because in order to have a center, there has to be at least three, right? So if there are only two atoms, that geometry is always going to be linear, right? Because if we think about a line is defined by, right, 2 points, right? And the polarity of this is always going to be based on electronegativity, which we'll talk about shortly, okay? If we have a central atom with two groups around it, right, examples would include CO2, for example, the molecule is going to be, the electronic geometry is going to be linear, the molecular geometry also linear, and again, polarity is based on groups, okay? If we have three groups, the electronic geometry is called Trigonal Planar, which means we have something in the center, right, and we have three things attached to it, and they're all in the same plane. That's what planar means, right? Now, if all of those things are atoms, right, then we end up with a shape that reflects that, right? This would be nonpolar, by the way, right? And an example of this would be SO3, right? In order to have something that is bent with two atoms and one lone pair, right, that means we would have a central atom, lone pair, and that's what it would look like, right? Wherein if we're comparing all three of these, right, we have the same basic structure, right? But even this last one, it's still 1, 2, 3 things around that central atom, yes, right? We have one lone pair, two single bonds, that counts as 3 total things, yes? Does it make sense? Okay, going back, 4 things would be called tetrahedral, right? Where if you look at your book, right, we have one up here, we have one here, and technically there's one that comes out of the paper, and then one that goes back into the paper, right? Tetrahedral. If they are all atoms, right, again, it's still called tetrahedral, right? CH4 would be a good example there, right? If 3 of them are atoms and one is a lone pair, right, something like NH3, right, we end up with that and a lone pair, and we end up with that, right? Or we could have something that's bent that has 2 lone pairs and 2 atoms, okay? Water being the classic example there, right? And then we get into these larger molecules where it's the same thing. I'm not going to draw them because I don't have space in those tiny boxes that I left. But 5 things would be called trigonal bipyramidal, right? Again, if they're all atoms, labels. This one would be polar. This is nonpolar. This one is polar. This one is polar. This one is nonpolar. And an example of this would be PCl5, right? 4 atoms and 1 lone pair would be like SCl4. That's called a seesaw shape. This one is polar. T shape, so 3 atoms and 2 lone pairs. 3 atoms and 2 lone pairs, right? So this would be something like IF3, polar. And linear would be something with 2 atoms and 3 lone pairs. So like XEF2, nonpolar. Octahedral, right? Here we would have like SF6, nonpolar. Square pyramid would be like IF5, a little bit polar. And square planar, XEF4, nonpolar. All right, so again, right, your here polarity, polarity, right? And so it might benefit you to go ahead and jot these down on your table, right? And that will be helpful to you, right? Do be mindful, right, when we talk about labeling something as polar or nonpolar based on this, right? We are making one huge assumption, right? We are making the assumption that all of the atoms that are bonded are the same, okay? We are making the assumption that all the atoms bonded are the same, right? So for example, if I'm talking about CH4, right, that is definitely nonpolar, right? If I was talking about CH3Cl, right, that's polar, right? There's a difference there. And when we start building some molecules, hopefully that'll become more clear. All right. Now, obviously you have to know this table in order to be able to sign whether or not a molecule is polar, right? Which goes back to, it would be helpful to make sure your review packet is done so that way, you get access to that note card, right? So determining polarity. So 1, shape matters, right? Shape determines polarity. But there's a secondary factor, right? And that has to do with our electronegativity, right? In that there needs to be polar bonds in addition to a polar shape, right? So one more time, polar bonds and a polar shape. And polar bonds, right, for the most part, so your book defines polar as being anything with an electronegativity difference in that range, okay? And when we say electronegativity, we simply mean the tendency of an atom to attract electrons to itself within a chemical bond, right? So fluorine is the most electronegative element, and it pretty much decreases going away from fluorine, right? Hydrogen being the one exception that should be over here closer to the nonmetals, okay? And this should make sense a little bit, right? Because when there's a large electronegativity difference, right, we end up with something that's ionic, right? And so if we think about that, when we think about ionic compounds, we're typically thinking about things from this side and this side coming together, right? So those are the things that are furthest apart on the table, which means they are furthest apart in electronegativity. So then it makes sense, right, that instead of sharing, there's actually a give and take, right? Polar covalent simply means that they share, but unequally, right? In a pure covalent, it means that they share equally. And there is a small range for that. Really, obviously, the only time there is a perfect sharing is if the 2 atoms are the same, right? So if we're talking about N2 or F2, right? But there are some bonds that are so close that we consider them to be nonpolar, right? So for example, anytime we have a CH bond, right, you can see that C is here, H is here, which puts us just at that 0.4 limit for being considered a nonpolar bond. All right. Now, in the land of how to take those 2 layers and put them together, right? When we think about carbon dioxide, for example, right? Carbon dioxide, we have a polar bond where this symbolism, right, talks about the polarity of my bond. This symbol means partial positive, right? So that's a lowercase delta. this is partial negative, right? And so the way the symbol goes is you put the plus on the plus end of a bond and the minus on the minus end, right? So if you're thinking about carbon and oxygen, oxygen is the more electronegative, which means that it attracts the electrons to itself more strongly. So within these bonding electrons, right, the electrons will spend more time closer to the oxygen, which is why we get this symbolism, right, which says that the carbon is the positive end and the oxygen is the negative end of that bond, right? Which then if we flip it to the other side, it goes in the opposite direction, which means that there is no net dipole, yes? There is no net dipole moment, which means the molecule is not polar, yes? Not polar because those two things cancel, right? It's like if you pull with equal strength on two sides of something, right? As long as those forces are on opposite sides, there's no net motion, right? Same thing. Whereas in water, right? So here, right, the positives are by the hydrogen and the negative is by the oxygen. And note here, right, and I think it's well done that they didn't draw the lone pairs, right? The negative is not because oxygen has lone pairs. The negative is because oxygen is more electronegative than hydrogen, yes? That's why the negative end is oxygen and the positive end is hydrogen. Now, there is a net force movement, yes, in that there is a net negative here and a net positive down here, which means that this molecule is polar. Yes, does that make sense? All right, tomorrow, or next class period, we will spend some time analyzing some structures and seeing if you can see for yourself whether a molecule is polar or not. All right, thanks for listening, be good, and I will see you soon. Bye.